Okay, welcome back. We are now busy with Chapter 4, Linear Programming. And in the previous lecture, we looked at a little bit of revision on how to plot a linear function. So in this lecture, we are going to look briefly at the history of linear programming, as well as the objective of a linear programming problem, and also the structure of a linear programming problem. Now, the historical context of linear program modeling lies in the field referred to as operational research. And operational research, or OR, is a relatively new field in the science, and it started in the 1940s in the United Kingdom. And the main driver for this research was the Second World War. The American Navy quickly took up from the British and used it for planning and research of military operations. The name operational research originates from this period. Today we use the broad term mathematical programming, which encompasses both linear and non-linear optimization. In this module, we are only going to focus on linear optimization. After World War II, operational research moved also into other fields like business, commerce, industry, and government, and is now used extensively in these fields. The range of applications for linear programming is enormous, but the basic problem is essentially the same. And the basic problem is that of choosing the best or the optimal solution from a large number of alternatives. We are going to restrict this course to linear constraint optimization, and therefore we call it linear programming models. But the field of application is extensive. Some examples of typical applications of linear programming are the following. The allocation problem. These problems deal with allocation of limited resources in the most efficient way. For example, if you have to allocate investment funding to projects so as to maximize the return on the investment, so that's the optimization, you would like to maximize the return on the investment, or else if you want to minimize the risk of the investment. Then the inventory problem, to provide answers to a simple question when and how much to order. For example, if you are a shopkeeper, you want enough products on your shelves so that your customers can find what they are looking for, but you don't want too much products on your shelves so that the products go past their expiry date. The scheduling problem, that would be the optimal allocation of processes in time and space. For example, finding the best examination schedule in a university, because you have to optimize in time so that there are no clashes, and also space so that there's enough space for the students to write their exams, because the venues are limited. If you think of the allocation problem again, let's say, for example, that you are writing a very big accounting and financial mathematics test the next day, and you have 10 hours left before these two big tests. So you would like to allocate your time to studying for these two big tests, but you also have to allocate some time to sleep. So you have to sleep in a minimum amount of time, and then you have to allocate the rest of the time between studying for the two different modules. So what we have here is we have to allocate your time between studying for the two modules as well as sleep, and you have limited resources. You have only 10 hours left. So then you would like to optimize your performance the next day in the two tests by allocating your time in the most efficient way between these three variables. That would be the time spent on sleep, the time spent on studying for financial mathematics, and the time spent on studying for accounting. So what we then do is we want to represent a real process like this with a mathematical model. Now, a mathematical model is a set of equations, inequalities, and functions that simplifies the reality. Now, I always say that a mathematical model is almost like drawing a cartoon character. You want to have the essential properties of a character in your cartoon drawing. If you have too little detail, then you will lose the emotion or the character of the person you are drawing. But if you put in too much detail, then you lose the base or the essential part of that character. So a mathematical model is a simplification in the same way as that a cartoon drawing is a simplification of reality, but the essential idea is still captured in that drawing. Now, when we set up a linear programming model, we have certain components. We have the decision variables, first of all, and the decision variables represent the unknown quantities that should be found by the decision maker. If you think back to our example of allocating your time between sleep, studying for financial mathematics, and studying for accounting, then your decision variables will be the amount of time spent on those three activities. In real problems, the decision variables are restricted in some or other way. So we have only 10 hours left before you write a test. So the time available, the total time available is restricted. You have only 10 hours. And let's say that we set a further restriction that you need at least 4 hours sleep to be able to do your best in writing these tests the next day. So the restriction would be the 10 hours allocated for all three of those activities, and you have to spend at least 4 hours on sleep. Now, when the optimal values of the decision variables are found, then we say that our linear programming problem is considered solved. Now, the next part of a linear programming model is the constraints. And we actually already explained that for our example, we say that the constraint is that we have a total of 10 hours before you write your test. And you also have to spend at least 4 of those 10 hours on sleep. Now, a set of all the values of your decision variables that satisfies these constraints is called a feasible point. And a set of all the feasible points is called a solution space or a feasible region. And we have to find our final solution within that feasible region. And then we also have the objective function. The objective function is a measure of the effectiveness of the system as a whole. So the objective function in our case would be some other function that reflects your total performance in these two tests that you are writing. So your function or your objective function will be a function of time spent on sleep, time spent on studying for financial mathematics, and time spent on studying for accounting. Now, suppose that accounting is the module that you are not so confident in, then one would expect that you should spend more time in studying for accounting than for financial mathematics, so as to maximize your final score in these two tests. Now, in the case when we want to maximize the objective function, we call it a maximization type of objective function. That would typically be something like performance, profit. That would be a maximization problem. Sometimes the objective function is a minimization type. For example, if you want to minimize something like cost or risk. Now on this slide I have a very simple example of a linear programming model with one inequality constraint. So the first function here, this first equation, is my objective function, and I've got two decision variables. I've got x1 and x2 as my decision variables, and I would like to maximize this function of x1 and x2. Now I have some constraints on this function. It's subject to 2x1 plus 3x2 less than or equal to 6. That's my first constraint. And then also there's the non-negativity constraint, which means that my x1 and x2 must always be greater than or equal to 0. You cannot have a negative solution for your decision variables. You will remember from our first lecture that we plotted the function 2x1 plus 3x2 equal to 6. Now we are working with an inequality less than or equal to 6. So how would we represent that on a graph? I'm going to go back to that drawing from our previous lecture. Okay, so that this blue one was the function 2x1 plus 3x2 equal to 6. But now we want to work with the inequality less than or equal to 6. I'm going to take out this red one here. We are now working only with the blue plot. So the inequality, to know, so now it is less than or equal to 6. So now we are not working with a line, we are working with an area. Less than or equal to 6, we want to decide whether it is the area above the line or below the line. Now to be able to do that, you choose a random point either below or above the line, substitute it into your inequality. If it satisfies the inequality, then you know that that is the area where the inequality will be satisfied. For example, if I take the point 1, 1, that is the point 1, 1. If I substitute it into this function here, I've got 2 times 1 plus 3 times 1, which is equal to 5. And it satisfies this condition, namely that it's less than or equal to 6. So we know that this inequality will be this whole area below the line. And remember, we also work with x1 greater than or equal to 0, x2 greater than or equal to 0. So that is why it's also restricted with these axes. Suppose I chose the point, let's say I chose the point 1, 2. If I chose the point 1, 2, it lies over there, and I substitute it into my equation, so it will be 2 times x1 is a 1, plus 3 times x2 is a 2, then it will be 2 plus 6, which is 8. It does not satisfy this condition, so we know that the inequality does not lie, it's not representing the area above the line. Okay, in this area, which we will call that area the feasible region. So the solution for x1 and x2 from our decision variables, the solution must fall within this feasible region. So we have many possibilities for x1 and x2 within this feasible region, but now to choose the optimal solution for x1 and x2 would be where we maximize for x1 plus x2. So we want to maximize that objective function within this feasible region. So the solution must fall within the feasible region where this objective function is maximized. So the general structure of a linear programming model will be the following. You have your objective function. You would either want to maximize or minimize your objective function. As I said, maximization will be something like profit. Minimization would be something like risk or cost. This objective function is expressed in terms of your decision variables. So your decision variables are these ones, x1, x2 up to xn. And the coefficients in your objective functions, the c1 up until cn, those coefficients are known from the problem statement. Then you have a set of constraints, and this is your set of constraints. You can see that your constraints are again expressed in terms of your decision variables, x1 up to xn, and the coefficients, the a coefficients, as well as the constants, the b constants, are also known from your problem statement. And then always this non-negativity constraint that all your decisions variables must be greater than or equal to 0. In the next lecture, we are going to look at ways in which you can solve a linear programming problem by hand.